Okay, so up until now, we've spent a lot of time talking about ideal gases, but it turns out that no gases are actually ideal. And although the ideal gas law gives us a pretty accurate idea of what's going on, there are slight deviations when we're talking about a real gas. And so what I want to do is I want to review the conditions of an ideal gas, and we'll see where these deviations for real gases occur. And first we said that an ideal gas is one that has molecules that don't occupy any actual space. So no actual space. And a real gas's particles do occupy space. It's a microscopic amount of space, but it's real. And a Dutch chemist named J.D. van der Waal actually studied this deviation. So van der Waal. And he also found that unlike ideal gases, real gas particles do exert a small amount of force on each other. And these forces were actually named after him. We call them van der Waal forces now. So van der Waal found that the degree to which a real gas deviates from an ideal gas has a lot to do with the magnitude of the intermolecular forces and the size of the particles. So let's draw a system and let's fill it with some particles. And what do you think is happening if all of the particles in this container are slightly attracted to each other? Well, in a small way, that gas is going to be imploding or caving in on itself. So caving in on itself because all of these particles are a little bit attracted to each other. And what do you think this is affecting? Well, it's going to affect the pressure because now the gas isn't pushing out on the sides of the container as much as we thought it was. So for a real gas pressure, we need to be able to correct for the intermolecular forces. But that's kind of tricky because we've got to think about what the intermolecular forces are dependent on. And first, I'd say that the extent of these forces is dependent on the concentration of the particles because more particles means more attraction. So the concentration of anything is just the amount of that thing per the space that it occupies. And the amount of our particles are the moles, and the space that they occupy is the volume. So the concentration is the moles per volume. And N divided by V, our moles per volume, would be alright if we're talking about all of these particles being attracted to one particle, but they're all actually being attracted to each other as well. So all of these particles are also attracted to each other. And what that means is that the force actually increases exponentially as particle concentration increases. And so we need to make it N divided by V squared. Now this is kind of a little bit of a crazy thought, but the thing that characterizes the intermolecular forces between particles is actually different for different particles. And so we need to account for the different characteristics of different gases and the atoms that are in their particles. So each gas has a different intrinsic factor that we need to consider, and we call that A. And we can think of A as the attraction coefficient, but it's usually a value that's given to us in a table because it's unique for the gases that we're dealing with. So putting these thoughts together, we find that the P ideal, the pressure ideal, is actually equal to the pressure observed plus this consideration of the attraction coefficient times the concentration of these particles squared. Now it's important to make note that the forces may attract each other. These particle forces may attract each other and cause the system to kind of implode, but they might also very well repel each other. And so if they repel each other, the value of A would be negative. So it can be positive or negative depending on whether the particles are attracted or repulsed from each other. And this makes pretty logical sense if you think about it, because the pressure we observe is an understatement of the ideal pressure if the system is slightly imploding. So we would need to add this correction. And it's an exaggeration of an ideal gas if the particles are repelling from each other and pressing out on the sides even more. And in that case, we would need to subtract the correction. So van der Waal taught us to correct for the intermolecular forces when we're dealing with a real gas. Now the other deviation was related to the size of the particles and the free space that they take up, which affects the value for our ideal volume. So each gas has particles that are a little different size, again, dependent on the atoms or the molecules that are in that gas. Hydrogen particles, for example, are quite small, but if we're talking about methane particles, well, those are quite a bit bigger. And so each gas has an empirical volume factor to consider for, and we call this factor B. And I usually think of B as my bigness coefficient, B for bigness. So we consider the size of the molecules, and we also have to factor in how many particles, molecules, or atoms there are, and that's just our moles, or N. So we multiply the moles by our bigness coefficient, and we can write this as an equation if we say that the volume ideal, the ideal volume is the volume of the container minus the space occupied by the particles, which would be N times B. And as another quick note, unlike A, B will always be positive because the molecules will always take up some amount of space. So starting with the ideal gas law, which is PV is equal to nRT, let's insert our corrected pressure for a real gas and our corrected volume for a real gas into the equation. So starting with our corrected pressure, we know that the ideal pressure is equal to the pressure observed plus our attraction coefficient times our concentration, our molar concentration squared. So P observed plus A times N over V squared. And then we can insert our volume. So the ideal volume is actually equal to the volume of the container minus the number of particles times the bigness coefficient, or B. So VC minus NB, and the corrected product of the real pressure and the real volume now is equal to nRT. So by correcting for the intermolecular forces and the volume that's taken up by the particles, now we have an equation that applies to real gases, which we call the van der Waals equation. And it looks pretty terrifying. There are tons of values in here, but it's really no big deal because the only difference between this and the ideal gas equation is just the corrected pressure and the corrected volume.